welcome back to Exam Ignite YouTube channel. This is Embedded System Design subject of VTU 6th semester module 1, where we'll be discussing about the introduction to embedded system. So here I have prepared the notes by referring to the textbook and the model question paper and the previous year question papers, that is December, Jan 25-26 or June, July 25 of the previous year paper. So here, firstly, we are starting with the what is an embedded system. So this is an important question where you will be expecting this question because you need to know the definition properly. Then the architectural block diagram has been asked in the model question paper. Then comes the classification of embedded system, the one more important question. Then major applications of areas of the embedded system, then the purpose of embedded system, the typical embedded system, that is course around the embedded system. Then you have to know you need to know the differences between the microprocessor and microcontroller, RISC versus CISC, Harvard versus one human, and big Indian versus little Indian, and also the memories, that is ROM and RAM types inside them. Then in the part 2 we'll be discussing this and the sensors and actuators, the input output subsystem along with the input output devices like light emitting diode, LED, 7-segment LED display, optocoupler, relay, piezo buzzer, then push button switch, and communication interfaces like onboard communication interface, where you'll be getting these questions in the previous year paper, as well as the external communication interface and embedded firmware and development, where along with the other system components where you need to know the brownout protection circuit and watchdog timer. These are all some of the important topics that we will be covering in the video. So let's move on to the embedded system. So firstly, define embedded system. An embedded system, it is an electronic, or you can say it's an electromechanical system designed to perform a specific function and is a combination of hardware and firmware, that is software. So it is an electronic, or you can say an electromechanical system that is designed to perform a specific function in the combination of both hardware and software. So it is designed for one specific purpose, combination of both hardware and software, highly specialized to the application domain. It can be used in the household applications, in the telecommunications, medical equipments, industrial control, and consumer products. Example is our home washing machine, microwave oven, air conditioner, television, DVD player, automobile control system. Next comes the important question, that is difference between the embedded system and the general computing system. So from the left side, we'll be seeing the general purpose computing system, and in the right side, the embedded system. So general purpose computing system is a combination of generic hardware and the general purpose operating system. Hardware is generic and the operating system is general purpose. In the embedded, it is a combination of specific purpose hardware and the embedded system. This executes a variety of applications. So here it executes a specific set of applications. This contains general purpose operating system. This may or may not contain an operating system. And here the applications are alterable, that is programmable by the user. But here the firmware, that is the software, is pre-programmed and non-alterable by the end user. The performance is a key deciding factor in the GPUs. In the embedded system, application specific requirements are the key deciding factors. These are less focused on the power consumption, but it is highly tailored for the power saving. Then here response requirements are not time critical, but here it is highly critical. Need not to be deterministic in executable behavior, but here it is execution behavior is deterministic. What are the examples we can see for the general purpose as PC, laptop, or tablet? In the embedded system, for the specific purpose like the TV, washing machine, microwave oven, then car control system. Coming to the history of the embedded system, so it has existed even before the IT revolution, and it has been built using the vacuum tube and the transistor technology with low-level programming languages in the earlier systems. So development in the semiconductor and nanotechnology and IT revolution led to the miniature of embedded systems. The first recognized modern embedded system was the Apollo guidance computer developed by the MIT Instrumentation Laboratory for the Apollo Moon mission. So these are some of the history about the about the embedded system. Next, we will move on to the classification of embedded system. So mainly they are classified based on four categories. One is based on the generation, second is based on the complexity and performance requirements, third is based on the deterministic behavior, and fourth one is based on the triggering. So first one is based on the generation. So first generation, it is built around the 8-bit microprocessor and the 4-bit microcontroller. Then it has simple hardware circuits with a firmware in assembly language. This was the first generation where the embedded system was. Example is digital keyboard, telephone keypads, or the stepper motor control units. Second generation, it is built using the 16-bit microprocessor and the 8-bit microcontroller. Here, the next step. It is more complex and powerful than the first generation system. This included the embedded operating system. So example is data acquisition system or SCADA systems. Third generation, it is used in 32-bit processor and the 16-bit microcontroller. Introduction to DSP, that is digital signal processor, and application-specific integrated circuit. Here, the processors become more powerful with the advanced instruction pipelines. So they are used in the robotics, media, industrial purpose control, and networking. Fourth generation here is introduction of the system on chip, that is SoC, recognizable processors, and the multi-core processors. So here it is high integration of the hardware components into a single chip, supports high performance real-time operating system. Example, you can give the smartphones, mobile internet devices. So second thing is classification based on the complexity and performance. Small scale embedded systems. So simple applications with non-time critical performance built using the 8 or 16-bit microcontrollers or processors may or may not contain an operating system. Example, an electronic toy. This is a small scale. In the medium scale, we are having moderate hardware and the firmware complexity that is built using the 16 or 32-bit microcontrollers or processors, usually contain an operating system. Next, the large scale embedded system, or you can say complex system, that is highly complex hardware as well as software used in the mission critical applications, that is built using the 32 or 64-bit processors, usually contain a RTOS, that is real time operating system for task scheduling and prioritization. Next is classification based on triggering. Here, event triggered, here activities within the system. Example, task run times are dynamic and depend upon the occurrence of different events. Time triggered, here activities within the system follow a statistically computed schedule, that is, they are allotted time slots during which they can take place, and thus by nature they are predictable. The major application areas of the embedded system are: first is consumer electronics in the camcorders, cameras, televisions, musical systems; in household applications like TVs, DVD players, washing machine, refrigerator, microwave, oven; then home automation and security systems, here air conditioners, sprinklers, etc. Then automotive industries, here it is anti-lock braking system, ABS, engine control, ignition systems, etc. Then telecommunications, here cellular phones, telephone switches, computer peripherals in the printers, scanners, fax machine, in the computer networking systems, that is routers, switches, hubs, firewalls; healthcare, here in the hearing aids, then scanners, ECG machines; then measurement and instrumentation, here in the digital multimeters, digital CROs, like this; then banking retail, we are using ATM; then currency counters, POS systems; then card readers, barcode readers; then wearable devices like the health trackers, fitness trackers, smartphone notification devices; then cloud computing and Internet of Things. Then what is the purpose of having an embedded system? So they are designed to serve one or combination of the following purpose. Firstly, data collection or storage or representation. Secondly, it is a data communication. Third one, for the data signal or the signal processing, monitoring, control, application specific user interface. So here, data collection or storage or represent. So embedded systems, what they collect the data from the external world, Data may be analog or in the digital form. So that collected data may be stored in the memory, that is, or processed by the system or deleted after the meaningful representation. They use display units like LCD, LED, buzzers, alarms for the representation. Example is our digital cameras, medical monitoring system. Next is data communication. Here it is used for transmission of the data between the systems. Communication can be wired or wireless. So wireless technologies include Bluetooth, Zigbee and Wi-Fi. Then wired interfaces include RS-232C, USB or TCP or IP, PS2. Next, here, what are the example? We are having network routers, switches, and communication modules. Data, that is the signal processing. So, embedded system process the voice, image, video, and the electrical signals. So, these are used in the application requiring signal processing. Functions include speech coding, audio, video coding, or signal transmission. Example is digital hearing aid. Next is monitoring. Here, embedded system monitor the variables continuously. So here they are used for observing or measuring the variables and not for the control. Example is in the ECG we can see we cannot alter. Then in the digital CRO or in the digital multimeter in the logic analyzers are the examples. In the controlling, embedded systems control the variables according to the input changes. So they contain sensors and actuators. Sensors capture the environmental changes and actuators perform the actions. So example is AC for a room temperature control. Application specific user interface. Here the embedded systems with the application specific user interfaces includes buttons, switches, then keyboards, display units, lights or bells. So example is our mobile phone user interface. Next is wearable devices, the innovation bonding of a lifestyle with embedded technology. So here we are having the wearable devices example like watch, bracelet, ring or necklace, etc. So what do they have? They combine the embedded computing and the communication, keep users continuously connected and updated. They track the fitness activities, heart rate, sleep, calories burned, etc. Then they provide a smartphone notification calls and messages. So these are all the features what those wearable devices do. Then what do they have? They have a embedded controller or a microcontroller in it, and also a wireless communication module, that is a Bluetooth or Wi-Fi. Then sensors, that is to heart rate or accelerometer, then temperature sensor or UV sensors. They have a battery and charging system to provide a continuous supply of power. Then comes the display and notification system. So working of these wearable devices. So sensors will collect the data such as a body movement or the vital signals. Embedded processor processes the collected data, and the wireless modules communicate with the smartphone or other devices. So information is displayed to the users through the apps or display units. So example you can see of the wearable devices is Fitbit. It is a fitness and activity tracking. So like then what are the application for our health monitoring, fitness tracking, and for the entertainment and gaming? So next comes a typical embedded system. So this is a question that had been asked in the model question paper, the architecture of the embedded system. So you need to write this as an answer for that. So typical embedded system consists of a single chip controller which acts as a master brain of the system. So controller can be a microprocessor or a microcontroller, DSP or ASIC or FPGA. So this is an elements of an embedded system where we are having a system core with a memory, communication interface, input port, output port, then other supporting integrated circuits and subsystems. So this can be any of the microcontroller. Now, what are the now we will be studying about the components of the typical embedded system. So first one is the core or system core. Here that acts as a brain of the system. Memory, it stores the program, data and the software. Input ports, that is the sensors. They take the input from the external environment. Output ports, that is actuators, produces the output or the control signals. Communication interface, they are used for the communication with the external systems. Then embedded firmware, that is a software embedded into the memory for the system operation. Then other supporting integrated circuits and subsystems, they are the additional hardware support required for the functionality of the system. So how does that work? Sensor collects the sensor connected to the input ports collects the data. Then the processor processes the data. Then using what? Using the software. Then control signals will be generated and that is sent through the actuator through the output ports. Communication interface will exchange the data with the other systems. So this is the working of complete embedded system. I have reduced it to 4 points and given. While writing, please to elaborate each one of the point and explain in your words. Examples of input and output system. Here input devices are keyboard, push buttons and switches or keypads that we use. Output devices are the LCD, LED, then buzzer or the speakers. Then comes the core of the embedded system. This is also a question that has been asked in one of the question paper. So the core of the embedded system is the central processing unit around which the entire embedded system is built. So this is the main brain. So categories inside this core of an embedded system is general purpose and domain specific processors, that is a microprocessor or a microcontrollers or a digital signal processors. Then comes the application specific integrated circuits, then programmable logic devices, then commercial off the shelf components. So first we'll be studying about the general purpose and domain specific processors. So nearly 80% of the embedded systems are processor or controllers. They are based. So the processor may be any one of this. So types, first one is what is microprocessor? They are used for the general processing tasks. Microcontrollers, they contain a CPU, memory, and peripherals in a single chip. TSP means it is used for the signal processing applications like the audio, speech, or image processing. First, we'll study about the microprocessor. It is a silicon chip representing a central processing unit that performs arithmetic and logical operations. What does that contain? It contains ALU, that is arithmetic logic unit, control unit, and registers. This requires external memory and peripherals for the operation. This alone cannot perform any types of operation. Example is Intel 4004. This was the first microprocessor of 4-bit. So then we are having Intel 8086 and so on. So general purpose processor and the application specific instruction set processor. So in that, general purpose means it is designed for the general applications. Application specific for a specific application. Architecture, here it is just generic, there it is optimized. Here, as it is a general purpose, it is of low cost, but that is costlier. Then this is used in the PCs and the common systems, that is used in the networking, automotive, telecom, and signal processing. Next comes the microcontroller. So microcontroller, it is a highly integrated chip containing a CPU, memory, peripheral devices in a single chip. So features are it contains CPU, RAM, ROM, or the flash memory, input output ports, timers, and counters. We have studied. So this requires fewer external components and it is low cost and compact in size. Example is our 8051 family, then PIC microcontrollers, AVR microcontrollers, or ARM Cortex series. So you need to know the difference between the microprocessor and microcontroller. This is an important question that has been asked in most of the question papers. So let us see that. Microprocessor, it is a single silicon chip representing a CPU capable of performing arithmetic and logical operations. Microcontroller, it is highly integrated chip containing a CPU, RAM, ROM, timer, and input output ports. Here it is dependent unit and it requires external chips like memory or interrupt controller. Here it is self-contained unit that does not require any external components. Here it is used for general purpose design and operation. This is application oriented or domain specific. This does not have built-in input output ports that contains. Here it is high performance is important, here used when the performance is less critical. Then limited power saving options. Here we are having power saving features. Next comes the digital signal processors. That is, these are the special purpose 8 or 16 or 32-bit microprocessors designed for a single processing application. So like faster than the general purpose microprocessors in the signal processing, these are designed for the high speed computation. What can the operations be done like addition, subtraction, multiplication, or division? So what are components? It has a program memory to store program, then data memory to store the temporary variables and the signal data, computational engine to perform the signal processing operations, input output units that captures and delivers the processed signals. Application here it is audio and video signal processing. In the telecommunication, in the multimedia applications we use. Next comes the RISC versus CISC processors or the controller. RISC is nothing but reduced instruction set computing, and here CISC is complex instruction set computing. This has a less number of instruction, here greater number of instruction, supports instruction pipelining and faster execution. Here generally no instruction pipelining. Orthogonal instruction set, here non-orthogonal. Operations performed mainly on registers. Here they are performed on the registers or memory. Large number of registers are available, limited number. Then program execution takes more instructions, but here it single instruction can perform complex tasks. Fixed length of instruction, variable instruction length, less silicon usage and pin count, here more silicon usage. Uses Harvard architecture, it can use any of the architecture. Next, Harvard versus one human processor or the controller architecture. So here Harvard is nothing but it has a separate buses for the instruction and data fetching, but here a single shared bus is used. High performance due to the parallel execution because simultaneously activities performed. Here it is lower performance, faster instruction execution, here slower execution, no memory alignment problems occur, but there it occurs. Then program memory and data memory are stored separately, but here they share same physical memory. Next comes Big Indian versus Little Indian processors or controllers. Little Indian is nothing but lower order byte stored at the lower memory address. Here higher and higher order byte stored at the highest memory address. Example you can see here byte 0, byte 1, byte 2, byte 3. This is a little Indian operation. Here base address plus 0, the base address plus 1, base address plus 2 and base address plus 3. Here this is how it is stored in the memory address as like this. Now let's see in the Big Indian. In the higher order byte stored at the lowest memory address. Now it is reversed and the lower order byte stored at the highest memory address. So you can see here, so byte 0, byte 1, byte 2 and byte 3 to the addresses. Next comes the load store operation and the instruction pipelining. Load store operation in the RISC processor, memory access is performed using the load and store instruction. So load instruction is transfers the data from memory to register. Store instruction transfers the data from register to memory, reverse. So this is the operation that occurs. Example you can see and go through the explanation given here. And next we'll move on to the instruction pipelining. Here it is a technique of overlapping the execution of instructions to improve the processor speed and performance. Like conventional execution follows the fetch, decode and then execute the sequence. So this is how the instruction pipelining goes on. Then comes application specific integrated circuit. So here it is a microchip designed to perform a specific or unique applications. So a features you can see designed for the application specific applications only. It integrates multiple functions into single chip, consumes less power and area, and used in the commercial products. Types of ASIC that we are having is custom and another one is ASSP. So next we'll move on to the PLDs, that is programmable logic devices. They can be reprogrammed to perform the different functions. We are having two types, one is FPGA and another is CPLD. FPGA is field programmable gate array and CPLD is complex programmable logic device. So they can be reprogrammed multiple times, used for designing, simulating and testing. They reduce the development time and they are flexible and cost effective. So next is commercial off-the-shelf component, that is COTS. So these are ready-made products that are used in the embedded system. They are available in the market and reduce the development time. They are low cost and for the easy integration they are used. Next we'll move on to the memory in the part 2 video of this module. So thank you for watching. Do like, share and subscribe to Exam Ignite YouTube channel.